Hi everyone, welcome to my video number 24. In this video, I'll talk on line integral, that independent of path. Independent of path. Okay, so what do we mean by this? If just give you a brief introduction on what we mean by line integral independent of path. Let's say if you have a line joining 2 points, let's say point A and point B. Let's make it 2 lines. Okay, let's say this is C1, this is C2. Now, if you integrate this over the C1, f dot dr, so which means we integrate from A from B using that path C1. Okay, now independent of path means that if we do the same integration but with different path C2, f dot dr, these two integral is equal, of course, provided that we need a certain condition that I will discuss later. So in this case, we call it the line integral is independent of path. If the condition is not satisfied, these two integrals will give you different value. Even we have a same function, same limit, but different path will give you different value. Right? In order to have the same value, it must satisfy the certain condition. Those certain condition I will explain later. So this is basically what we mean by line integral independent of path. So the advantage is that we may choose any path, any line, any path between connecting A and B that's supposed to be help us to work much more easier. All right, so this kind of integral depends only on the initial point and internal point, initial and terminal points. Initial point and terminal point. Okay, right. So before we discuss further, I would like to give you some related definition that we might use later on, or you need to know that. A curve is called closed. A curve is called closed if its terminal point coincide with the initial point. Coincide with the initial point. So, which means position vector A is equal to position vector of B. So in other words, I can say if this is a point A, after some time we move around and then it's come back to this. This is also B. Okay. Of course, here at t equal to, let's say, t naught. For B, t equal to t sometime. All right. Let's see. Okay, so that's a first definition. Next, we define the open region. Yeah, we say that the region D is open if for every point P in D, okay, there exists a disk with center at P that lies entirely in D. So what do we mean by this? Let's say if we have a region, this is our region D. If we pick up any point in D, so let's say this be P. So at center at P, we can develop, or we can have disk that center at P that contain entirely in D. So this, let's say radius epsilon. So this of radius epsilon. Okay, if the boundary goes beyond than the boundary for D, then this region is not closed anymore. It's just the same concept in real line system. If you can recall this, in the real line system, we call this interval open. We denote as that. What does it mean? So X cannot be on the boundary. So if we pick up any point inside the interval, we can always have the small interval which contain entirely in that interval I. So let's call this interval I. Let's call this interval I. So in that case, we call it as a open interval. So the same concept here. If the disk contain entirely in the region D, then we call region D as a open region. Alright. Another definition. We say the region D is connected. The region D is connected. If any two point in D, any 2 points in D, any 2 points in D can be joined by a path or a line that lies entirely in D. So what do we mean by this? So if you have, let's say this is our region D. Okay. Then if you have a 2 point in D, let's say this is point P1, this point P2. Okay. Then we can connect these 2 points P1 and P2 with a path, with a line, that with a curve, whatever you want to call it, that this curve contain entirely in D. Okay, we cannot have something like this is 2 point, then goes out and then coming back here. So this is not connected. We don't have this kind of thing. And another thing is, we have, let's say we have D is given as a like that, the union of two region. So we have 1 point here, 1 point here. If you connect these 2 points like that, this is also not connected because it goes at some point it goes outside the region D. So in this case, the line or the curve or the path not contained entirely in D. So this is not connected. This case, so this is connected. But in this case, of course, we don't use this because we still have a choice. We still have a choice to find a path that contain entirely in the region D. Okay. Now, another definition. Another definition. A simple curve. A simple curve. Simple curve is a curve. That does not intersect itself anywhere between its endpoint. So we have for the closed curve or simple closed curve. For closed curve, we have RA equal to RB from the previous definition. Right? But at any 2 points between A and B, R T1 always different than R T2, where we have A, T1, T2, B. Alright. In other words, in the simple words, we cannot have something like this. This is point A, this is T equal to A, this is T equal to B, and if you have T1 in this case, T1 is there, T2 for the we move on, so this is T2, so in that case T1 equal to R2. So in this case, this is not simple closed curve. Simple closed curve always look like this. That. Okay, this is simple closed curve. So it's not intersect. And another definition, that a simply connected region, okay, is a connected region such that every simple closed curve in D enclose only points that are in D. Okay, so this is simple closed curve, simply connected region. This is not simply connected region. Okay, if our region is like that, so this is not simply connected region. This is also not simply connected region, and so on. Okay, easy to say. If for the simply connected region, if we pick up any point inside that, okay, and then you make those regions shrink. You shrink that region until it approach that point, so that region will not stuck anywhere. So that means simply connected. In this case, if we pick up a point here, if we shrink that region, so that region we cannot pass that vacuum, I would say. All right, it cannot pass that point in order to reach that. So in this case, this is not simply connected. Okay. Then we go to the definition. A theorem. Suppose that F is a continuous vector field on an open connected region, if C dot dr, if you integrate C F dot dr is independent of path, in D, then F is conservative, TIV, okay, conservative vector field on D. That is, there exists a potential function f such that del f is equal to f. So this point is very important here. Okay, so first thing is we have two terms. First thing is the integration is independent of path. The second thing is f is conservative. I think, if I'm not mistaken, I have given the definition of the conservative vector field. What do you mean by conservative vector field? In the previous, I forgot the what video is that. So if you look at the this condition, if you look at that condition, sorry, we don't have dot here, just that. If you look at that condition, that equal to f, okay, and we consider a vector field f with component, let's say P and Q. So what we can see here is that del f is, you may consider 2-dimension, 3-dimensional. For this case, I just show for the 2-dimensional case. So we have del f is fx, fy. Yeah. Then this is equal to, our f is given as P and Q. So that means we have fx or del f del x, right? Del f del x, that equal P, and fy equal to Q. Del f del y equal to Q. I can differentiate this with respect to y. So if you differentiate that with respect to y, so we have del 2f del x del y. This is del p del y. For that, I can differentiate with respect to x, that gives del 2f del x del y. This is equal to del q del y. sorry, x. That one is x. Okay, so you can see here, this is del f del x, del 2f del x del y. This one is del 2f del x del y. And since f is continuous function, then these two components are equal, which means we have del p del y is equal to del q del x. So this will give us very important condition that if the vector field is conservative, then this condition must be satisfied. So in order to show that our vector field is conservative, we need to show that this condition must be satisfied. So that's the importance of that relation. Now, and we have, I think this is another theorem. Okay, we have another theorem. Okay. Let F vector field with component P and Q be a vector field on an open simply connected region, be a vector field on an open simply connected region, D, and suppose that P and Q have continuous first derivative, continuous first derivative means we can differentiate P, differentiate Q once, and it's still continuous. And we have the condition del P del Y is equal to del Q del X. This is we derived just now. Then throughout D, then we say F is conservative. Okay, and the function f that satisfy this, the function, the scalar function f that satisfies this relation, we call as is called the potential function. Yeah. Now let me give an example how to find those potential function and how to use the conservative vector field. Okay. Example. Is a vector field given as 3 plus 2xy x squared minus 3y squared is conservative? Is that conservative? If so, find f such that del f equal to f and hence evaluate C f dot dr where C is any path from 0 to 232. Okay, so we have three questions here. First thing is we need to determine whether this vector field is conservative. The second thing is if so, we need to find the potential function f, and hence if it satisfies this, which means this integral is not independent of path, then we can use any C that connecting 2 points in order to evaluate those integral. Okay, all right, so let's do this. We begin with that to show that del f the vector field is conservative. What we need to show is del p del y is equal to del q del x. If you forget this relation, let's say if in the exam you forget the relation, you can always obtain this by follow this step that I've mentioned earlier. That step. Okay, just differentiate once with respect to x and y, and then equate both. So we can obtain those relation. Okay, so identify this, which one p, which one q. Don't change this. This is p, this is q. Don't change the position. So p, our p is 3 plus 2xy. Our q is x squared minus 3y squared. So del p del y, so you can see in this case is 2x. Here del q del x is 2x. So this is also equal to del q del x. So they are equal. So therefore f is a conservative. Therefore S is conservative. Okay. All right. Now, in order to find, we want to find a potential function f. Okay. So we begin from that relation. So we have del f equal to f. We begin from that. Okay. So what is del f? Del f is del f del x, del f del y. Our f is given in the questions 3 plus 2xy x squared minus 3y squared, and these are vectors. So two vectors are equal if each of the component equal. So del f del x will equal to that, del f del y will equal to that. So that gives us a relation. So we have del f del x is equal to 3 plus 2xy, and del f del y is equal to x squared minus 3y squared. Okay, now we can start the process to find what f is. From there, we need to use that relation. So we need to find f. In order to find f, so let's call this equation 1. Let's call this equation 2. Just we give a name there. So from 2, if we integrate 1 with respect to f, with respect to x. Integrate 1 with respect to x. So what we have a function f. So that gives us 3x plus here x squared over 2 to cancel out x squared. Cancel out y. And we have some constant. We have a constant. So this constant is of the form y. Okay, why not c? Why not c? Because in this case, y is a constant with respect to x. Remember that if we integrate this, we obtain this f. We differentiate that with respect to x, then we must get 1. So if you differentiate this function with respect to x, you have 3 plus 2xy. This is 0, so that gives you 1. Okay, now we need to find phi. How to find phi? We're going to use 2. So what 2 says? df dy. So which means we need to differentiate that with respect to y. So if we differentiate this function with respect to y, you remember that f is a function of x and y. Okay, where f is a function of x and y, means we can differentiate with respect to x, we can differentiate with respect to y. So we differentiate that with respect to y, del f del y, that gives us, that one is 0. Alright, so that one gives you x squared. That one you got del phi d phi dy. Okay, and this equal to that equation, equal to 2. Equal to 2, that. So which is x squared minus 3y squared. Why equal? Because this is df dy. This is df dy. So they are same. Okay, so from this, you can just simplify that. Then we have d phi dy. This is equal x cancel out. So we have 3y squared. We want to find phi. The purpose is we want to find the phi. Then we need to integrate this. So integrate phi. Integrate d phi dy with respect to y. So we will have this negative y cube cancel out. So we have y cube plus. Now we have a constant. Now this is a real constant. We cannot put x here, cx or phi 2x or whatever, because in this case x is already gone. So just a normal constant c. Okay, so we find f phi. So therefore our f is 3x plus x squared y plus phi y is given by this. So negative y cube plus c. So this is our potential function that we are looking for. Now, if there is a need to find c, of course we need the initial condition. Without the initial condition, we cannot find c. So in this case, just leave it the answer like that. Okay. Now, for the next question that we want to evaluate cf dot dr, and we have shown that our vector field is conservative. So what we need to do is that these integrals depend only on the initial and terminal points. So which means in this case, the function, the evaluation of this, we just evaluate f at point 3, 2 minus the initial point 0, 0, 2. Use the function f that we obtained, the potential function. So you can just evaluate those things, just substitute that into that, substitute this into that, you got whatever value. So this is the value for that. You can always check this is true or not. You just connect 2 points, let's say 0, 2, another point is 3, 2. You can connect, say for example, a straight line. You can find the equation of that straight line. You can have x equal to what? Y equal to what? Of course, in this case, depend on t. In this case, depend on t. You know this, how to find the straight line. Okay, and then you can find dx in terms of t. You can find y in terms of t, dt, and then you can just substitute into that, because those C f dot dr, this is just C, f is P, Q, our dr is dx, dy, then we have C P dx plus Q dy. You have dx here, you have dy here, substitute into here, then we have all terms here in term of t. So you just need to integrate with respect to t. So the answer, this will give the same answer to that case. You can try this. Try yourself. Do it yourself as a check. Okay. I think we stop here for this, for video number 24. All right. Thank you. Bye.